down, take a seat somewhere. There's an empty one over there, and there's an empty one on that side. Okay, all right. Well, we have to get started. So let me start by saying I'm sorry that I'm a tiny bit late. It won't happen again. I started this morning by just going to the other venue so that the whole class has seen me, the whole class knows who their course convener is. Okay, so let's do some of the administrative stuff first. So welcome to MAM2084S. I'm your instructor and I'm also the course convener, Thomas van Heerden. My details, there we are. Thomas van Heerden. I've got an office in this building. It's M101.6. It's on the bottom floor in the corner. And if you need to email me, my email address is just thomas.vanheerden@uct.ac.za. You might need to email me if you, for example, have any administrative queries that aren't covered by the course information sheet, if you have to provide medical certificates, all of that admin-related stuff, you should bring it to me rather than to the other lecturer. Lectures, well, Tuesday to Friday, and you've clearly found the venue. I will wait, I guess, till next week before we organize sort of fixed office hours, fixed consultation times. I realize you've got lots of pracs and labs and things to sign up for, so once you've done that, once your timetable is finalized, we'll try to work out something which is suitable for everyone. We have tutorials every week. You've got to come to those tutorials. They're compulsory. First tutorials happen this afternoon. If you haven't already done so, please go to Vula. There's a tab on Vula, I think it's called Section Info, where you can sign up for tutorials. I believe there are 424 people in the class and 420 spots available on Vula. So if you're one of the last 4 people, just send me an email and we'll work something out. I'll manually add you to an appropriate tutorial slot. But please, if you haven't yet signed up for a tutorial, do that. We want you to sign up on Vula so that we can print out accurate registers so that we know who's supposed to be in each tutorial venue. Attendance at those tutorials, like I said, is compulsory, and you have to attend at least, I don't know what, we've got 12, so you've got to attend at least 11 of the 12 tutorials. If you don't attend 11 of the 12 tutorials, you'll be DPR'd and you'll fail the course. And I realize this seems maybe a little bit strict, but this is the only thing we ask from you, right? We don't have weekly problem sets that you have to hand in. We don't have practicals that you need to do. We don't have lab reports that you've got to write. All you need to do is come to the tutorials and work through the tuts, right? So we're going to take this fairly seriously. Okay. The syllabus and the textbook, we can maybe talk about those at the same time. There is no textbook, but I've uploaded a set of notes to Vula. It's a set of notes that I typed up based on the lecture notes I wrote out last year. If you notice any typos or any mistakes, any errors, it's quite likely that somewhere there are algebraic errors or missing signs or whatever. If you notice any of those mistakes, please send me an email and I'll correct them. And then I guess if we just go to the notes, you can see that there's a, where are the bookmarks? There we go. Wait, no bookmarks. Oh, there we go. They're the bookmarks, right? So if you go to the notes, also available in Vula, you can see that there's a set of bookmarks associated with this, or you can just go to the table of contents, and that will give you a fairly decent idea of what we're doing in this course. So it's an introduction to linear algebra and differential equations, and you'll see that the differential equations, linear differential equations, provide a really good motivation for why we need all this linear algebra. We have 2 class tests during the semester, and the times and the venues have already been confirmed. So on the 18th of September and the 27th of October in the evening, we have the class tests. We have those venues. What we haven't done yet, and what I'll do closer to the time, is work out which students are going to go to which venue, so that will probably just be done alphabetically. All right, so if you're near the beginning of the alphabet, you'll go to Leslie 2A. If you're in the middle, you'll go to NLT. And if you're near the end, you'll go to Snape 1 for the first class test. And something similar for the second class test. All right. The marks, the final marks for this course, you need a 35% for your class record. That's just the average of the 2 class tests to be awarded a DP. And then your final mark is calculated from your class record and from your exam. we weight that so that it favors you, right? So if you do well in your exam and badly in your class record, then your class record counts for 20% of your final mark and your exam counts for 80%. If you did better in the class tests than you did in the final exam, then the exam will only count for 60% and the class record counts for 40%. But whatever you do, the exam is going to be a fairly large contribution, right? You can't get away from that, so you're going to need to perform in the exam to pass the course. But you really shouldn't be worried about that. I realize that the course it may seem quite abstract and very different from the courses you've already done, even from things like MAM2084. And you may at the start of the course feel a little bit lost, like you're not 100% sure what's going on. That's fine. It's been my experience that by the end of the course, most people are thinking in the right way, and they pass, and they pass quite well. Okay. So having said all that, let's actually just see, are there any questions about all these administrative arrangements before we go on to the maths? No. All right. Okay, so we're going to talk about the mathematics. So section 1, introduction. Well, in fact, not introduction, section 1, fundamentals. And the first thing we're going to do is section 1.1. We're going to talk about vectors and vector spaces. That we're going to ask is the following, right? What is a vector? You guys surely have seen vectors at some stage in your undergraduate degree so far. Can anyone tell me what is a vector? No takers, yes.
Magnitude and direction.
Sure, it's a quantity with both magnitude and direction, and that's a very physicsy sort of answer, right? So if you're a physicist, quantity with magnitude and direction. And you may also then have seen sort of in first year, maybe if you did 1042, if you did the statics course, or I guess even in 2083 you did vector calculus, sort of early mathematics. You may think of a vector as being an element of R3. So something like this, 5, 1, minus 2. Right, you might think of that as being a vector. We're going to provide a more general definition, a more general description of vectors, right? And the reason we do this is it's a little bit harder, right? It's a little bit harder to get your head around this more general, more abstract definition of what a vector is. But every time in mathematics when you generalize, all right, every time in mathematics when you generalize, you end up getting something for free later. And what we're going to do in this course is we're going to introduce this notion of vectors, and we'll see that some of the vectors are these sort of familiar objects, right? These are vectors in R3 or R4 or Rn, and we'll be able to prove some results involving these vectors, and then we'll start speaking about differential equations, and we'll see that many of the results that we can prove using sort of linear algebra on these vectors in R3 carry over, and we can sort of find analogous results with very little work when it comes to differential equations. So there's an initial upfront cost when you generalize, when you work with a more abstract definition. There's an upfront cost. You've got to get your head around it. But later on, it means that everything you know about one sort of instantiation, one sort of particular application of that general idea can then easily be translated to other fields, right? So we're going to use a slightly more rigorous definition. Okay, we use a slightly more rigorous definition. This is not a completely rigorous definition. If you want the completely rigorous definition, and some of you might, you can take a look at Wikipedia and they give you a proper set of axioms. So we use a slightly more rigorous definition. Rigorous. Okay, and I'm going to try to do this in a sort of consistent way. When I define things, we're going to get def over here, and then the thing that I'm going to be defining, I'll write in green. So we say a vector space so vector space V is some set generally it's an infinite set, so a vector space V is a set that satisfies a vector space is a set that satisfies the following two conditions. The first condition is that you should be able to take any two elements in that set, and we're going to call the elements of a vector space vectors. You should be able to take any two vectors in the space, add them together, and the result should be another vector in that space. And we call this, we say that the vector space should be closed under vector addition. So satisfies the following two conditions. For any two elements of V, we call the elements of V vectors. For any two elements of V called vectors, U and V, right? The sum U plus V should also be an element of V. And there's actually sort of an implicit claim being made in this statement. We're not just claiming, explicitly we're claiming that we've got these two vectors, and if we add these two vectors, the result should also be in the vector space. But there's an implicit claim, which is that if we've got two vectors, there's some way of combining them, right? So we'll have to sort of think a little bit about what vector addition is, and vector addition might look slightly different in all our different vector spaces. And then the second condition is called, in fact, let's write down what this is called. This is also called i.e. V is closed under vector addition. V is closed under vector addition. The second condition is that if you take any vector in our vector space V and you multiply it by a scalar, and generally to each vector space is associated a different set of scalars. For the most part, we're just going to use the real numbers as our scalars. But you take any vector, you multiply it by any scalar, and the result is again a vector inside your vector space. So this is just closure under scalar multiplication. So for any element of V, well, let's just say any vector in V, and in fact for any vector V in V, any vector v and scalar alpha, usually alpha is going to be a real number, not always. Usually alpha is a real number. So for any vector v and a scalar alpha, the product, alpha v, is again an element of v. Okay. And this is a closure under scalar multiplication. So let's write that down as well, i.e. v is closed under scalar multiplication. Yes. Yes. So that should be a vector v. Yeah. That's scalar alpha multiplied by my vector v. Yeah, I mean, different people denote vectors differently. I'll, for the most part, use underlines when I'm writing it out. And when we are typing it out, we'll use a boldface. Some people put arrows on the top. You can do that, but it gets a little bit complicated because you want to use the top later on to indicate conjugates. So I generally try to use an underline. Okay. So we have some definitions of what it means to be a vector space and what it means to be a vector. What we can do now is we can actually take a look at some examples and see if this sort of definition, a slightly more rigorous definition of a vector and a vector space, agrees with our intuition. Okay, and examples I think we'll do in this color. So what we're going to do is we're just going to show that R3 is a vector space. If we want to show that something is a vector space, we have to show that it satisfies these two conditions. We've got to show that it is closed under vector addition. We've got to show that it is closed under scalar multiplication. So what I'm going to do first is I'm not going to show that it's closed under vector addition and scalar multiplication for an arbitrary vector and scalar, which is what we should do. I just want to give you a sort of concrete example of what vector addition looks like and what scalar multiplication looks like in this vector space. I mean, we've got a pretty good idea of what it looks like, I think, but let's write it down. Okay, so let's just start with some informal intuitions. So we have some informal intuitions about R3, and one of these intuitions might be something like this. If I take this vector, 1, 2, 6, I can add it to this vector over here, 4, -3, 0. And many of you may have a very strong opinion on what the result is going to be when we do this addition. So does anyone want to tell me, what do I get when I do this addition? Okay, well, what do I get up here in the top? 5. Okay, and then next, -1 and... All right, okay. So we've got this intuition that if we want to do vector addition in R3, we simply add the components. So we take the x component and we add it to the x component and we get a new x component. And the y component is the same and the z component is the same. And in fact, maybe we shouldn't call it the x, y, and z component, because then we are thinking in R3. In general, we're going to take the first component and add it to the first component. Second component to the second, third to the third, case to the case, all the way down. We might also think that we've got some idea of how to do scalar multiplication in R3 already. So if I were to take, let's say, -2, and I multiply it by 1, 2, 6, what is that going to be equal to? Okay, so you're all mumbling quietly under your breath. That's fine. -2, -4, -12, right? So we say that if we do scalar multiplication, we just multiply each entry by that scalar, and that's the new entry. And if we take a look at this, right, when we added those two vectors, those are two vectors in R3, they each have three components, each of the components is a real number. The result was an object with three components, each of the components was a real number. So when we added these two vectors, the result was again a vector in R3. And the same things happened over here. We could multiply by this scalar, and the result is an object with three entries, and each of those entries is a real number. So it looks like we've got something which is closed under scalar multiplication as well. Right. But this is sort of very informal. You can't prove something is true by looking at examples. If you want to prove that something is true, you've got to present some sort of argument which is valid in the most general case. So that's what we're going to do now, right? So here's a general example, sort of argument. So the general argument might be something like this. Let's start by writing down R3. So R3 is a set. It's a set of things. It's a set of things, let's say X, Y, Z. It's a set of things which have three components. And these three components, X, Y, and Z, they're all real numbers. What we're going to do now is we're going to choose two arbitrary elements of R3, add these arbitrary elements together, and check that the result is again an element of R3. So if we take an arbitrary element in R3, if we take down just, let's say, let U and V be elements of R3, then I'd like to write down U is equal to something. And I don't know exactly what U is equal to, but let's just write it down something like this. Ux, Uy, Uz, and I know that Ux, Uy, Uz they must all be real numbers. Okay, so I've written down a very sort of general vector U. Similarly, I can write down V. V1, V2, V3, or that is V. V is equal to V1, V2, V3, where, oh no, not V1, I'm using Vx, Vy, Vz, where Vx, Vy, Vz, these are all real numbers. And if I add these two together, if I take U plus V, U plus V is equal to Ux, Uy, Uz plus Vx, Vy, Vz. And that's equal to, I said we'd just do this element by element, Ux plus Vx, Uy plus Vy, Uz plus Vz. That's the result of doing the addition. Now I want to check whether or not this thing that I produced, this vector that I produced by adding these two, is actually an element of R3. If it is an element of R3, great. Then R3 is closed under vector addition. If it's not an element of R3, well, then it can't possibly be a vector space. So who thinks that this over here is an element of R3? Okay. So why is it an element of R3? Anyone want to suggest why? Yes? All its elements are real. Okay, and all its elements are real because the first element, Ux plus Vx, is just the sum of two real numbers. And when you take two real numbers and you add them together, you get another real number. Okay, all right, so we can say that this is an element of R3 since the sum of two real numbers, Ux plus Vx, is again real. Okay, that's the basic idea. We can now conclude, I guess we write down one line here, V is closed under, or R3 rather, R3 is closed. R3 is closed under vector addition. Great. The next thing that we've got to do is we've got to show that we have closure under scalar multiplication. So again, we choose an arbitrary vector. In fact, we've already got an arbitrary vector. We're going to use u, say. Now we choose an arbitrary scalar. In this case, we'll call it alpha. Alpha's been arbitrarily chosen. It's not 3 or 5 or pi or minus 2. It's just alpha is some real number. Alpha u is going to be alpha multiplied by ux, uy, uz. And that's alpha ux, alpha uy, alpha uz. And you can take a minute, write something down here. Write something down over there, explaining why this must also be an element of R3. And you can take a look at what we've just written down for the vector addition. Write something down explaining why this is closed under scalar multiplication. Okay, so why is this thing an element of R3? Exactly, we write here, since the product of two real numbers is again real. R3 is closed under scalar multiplication. And now that we've said R3 is closed under vector addition and R3 is closed under scalar multiplication, we might conclude here R3 is a vector space. Right, we've shown that these two things these two conditions are satisfied. Yes?
I'm just wondering whether we need to say anything about the number of elements in the vector that we're
Oh yeah, it is critical. I guess I've sort of maybe brushed over it because it seems quite obvious, but yes, we should maybe point out that here we've got 1, 2, 3 elements in our result, and here again we've got 1, 2, 3. So maybe we can write something here as well, yeah. In fact, I'm just going to leave it like that. That's enough. Those boxes, we're making it quite clear. We've got 3 different elements over there. Okay. Any other questions? Yes. Are there no finite values of vectors in a vector space? Do you mean? I'm not 100% sure what you mean. Do you mean like? Clearly, the answer to that is yes. There are finite valued vectors in a vector space. Like this 5 minus 1 6. This is a vector with finite values in that vector space. Is that what you were asking? All of the vector spaces that we're going to look at are vector spaces with an infinite number of elements in them. If we have time today, I will do an example of a vector space which has a finite number of elements in it, but they're interesting, but they're interesting for different purposes than the purposes of this course. Okay. Yeah, but I mean, so whenever the scalars associated with a vector space are the real numbers, you immediately end up with an infinite number of vectors in the vector space because your scalars are infinite. And all the scalar multiples have to be in there. All right. Okay, maybe at this stage it's worth sort of pausing and thinking about, we've got R3 over here and we've seen some operation on R3 addition where R3 is closed under addition. Can anyone think of an operation on R3 that R3 is not closed under? Yeah, someone over there said it. What was it? Dot product, right? So the dot product, R3 is not closed under the dot product because you take two elements of R3 and you combine them using the dot product, the result is a single real number, which is not an element of R3. Okay, so it's not the case that, I mean, it seems sort of obvious looking at this, everything must be closed under everything else. No, it's not the case, right? Dot product, for example. Yes?
What do you mean when you say closed?
Closed, the result is the same type of thing as what you put in. So, dot product, you put in two vectors, and you get a real number out. So it's not closed under the dot product. Okay. Yes? Okay, yeah, sure. If you multiply by a complex number. Then, that's sort of strange in the sense that we wouldn't really ever use the complex numbers as the scalars associated with R3. But we could use the complex numbers associated as the scalars with C3, where you've got three complex entries. And then we do have closure again. But yeah. All right. So let's keep going. Let's take a look at another example. And this is an example which will be quite important in this course. And that's just R sort of raised to R. And what this is simply the space of all functions which accept all the real numbers as inputs, and your outputs are some real numbers. Okay, so this is just the space over here. Space of all functions is a space of functions we can write it down maybe a little bit more directly than this. So it's all the functions f such that f takes in a real number and gives you a real number. Okay. So it's a space of functions, it's a space of all real valued functions. So what we should think about now is this a vector space? In fact, yeah, let's write that down. Show that this is a vector space. Okay, show that this is a vector space. And this is how we define it. So the first thing that we should check is that we should check if we add two vectors, if we add two functions, the result is again a function, and it's still a function which accepts a real input and gives you a real output. And maybe it's worth just stopping for a moment and thinking about what are we doing when we say we add two functions, right? So let f and g be elements of this function space. What is this new object that we're creating, f plus g, right? Can anyone or does anyone want to make a suggestion for how might we define this new vector or this new function f plus g? So if I say I've got f plus g, and I want to know what does f plus g do to some input x? Yes?
So f plus g is the sum of the outputs that we get for every given input.
Yeah, it's just simply the sum of the outputs. So over here, if you want to know what does f plus g do to some input x, well, it calculates the output f of x, and it calculates the output g of x, and then it adds those two outputs together. Right? It does something which I think is sort of fairly natural and fairly intuitive. So now we've got to convince ourselves plus g, this new object, f plus g, is a function from the reals into the reals. Well, maybe the second part, the outputs, are pretty obvious, right? F of x plus g of x, well, f of x is a real number because f was originally in our space, and g of x must also be a real number because g of x was originally in our space, right? So those are the outputs from f and g individually must be two real numbers. So when we add those two outputs, we're just adding two real numbers. So this over here, f of x plus g of x, is again the sum of two real numbers, which means that f of x plus g of x must be a real number. So the output over here is a real. So we'll say note that f of x plus g of x is a real number since it's the sum of two reals. And the second thing that we should notice is that that expression that we've written up over there for this new object f plus g, that expression is well defined for every single real value of x, right? So we can actually define this for every real value x. And it's defined for every real value x because each of these individual pieces, f of x and g of x, are defined for every real value x, right? And we know that f of x and g of x must be defined for every real value x because they belong to this space of functions, which takes in any real number and gives out some real number, right? So we sort of just rely on the properties that are inherited from the original functions we're adding together. So we've got something like this. Therefore, f plus g is a function from the reals to the reals, i.e. f plus g is an element of this set. And we might now say, if we wanted to, I'm going to skip it because I'm lazy, we might say RR is closed under vector addition. So we've got vector addition, yes.
Do f and g have to fill the entire vector space? As in, if g or f isn't defined for a certain set of numbers, so you're dividing by zero in certain cases, is that not an element
Yeah.
of a function of
Yeah.
the vector space?
So if f was, for example, tan of x, right, and tan of x isn't defined because it's got all these asymptotes. If f was tan of x, you wouldn't be able to find it in that set to begin with because it doesn't meet the requirement that its domain is the entire set of real numbers. Okay, so the fact that f and g were taken from this space guarantees that the domain is the entire set of real numbers. All right, any other questions? Okay, so we've got a tiny bit of time. We can finish off this example. So the next thing we should do is we should check scalar multiplication. So we'd say something like let alpha just be some real number. These again are the sort of very natural scalars associated with this space. Let alpha be a real number. And then we'll say something like this. Alpha f. What are we going to do? This new object alpha f, what is alpha f acting on x? Yeah, exactly. So this will just be alpha multiplied by the output of f. And since alpha is a real number and f of x is a real number, this must be a real number. Okay, so we'll say something like this. Okay, let's notice that this is going to be true for every real number because f of x was defined for every real number, and alpha times by f of x, element of the reals. So r to the r closed under scalar multiplication. And we've got a couple of minutes left, so I'm very quickly just want to show you one example of a vector space, which is a finite vector space. It's a vector space which only has 8 elements in it, not an infinite number of elements. It's not a vector space we're going to work with much in this course, but it is a vector space which turns out to be really useful. And it's this vector space here, and you can take a look at the notes if you're interested and you can get a better sense for it. There's this space over here, which is the space of binary codes of length 3. This space of binary codes of length 3 turns out to be really important, especially if you're doing electrical or computer engineering. You're going to need to understand a little bit about binary. Just a little bit, right? F2 over here is simply a set which has just got 2 elements in it, 0 and 1, right? Not very interesting. Then F2, 3 is a set of the following form. It's got 3 entries. Let's call this X, Y, Z again. But now X, Y, Z, instead of being real numbers, they're elements of F2. So if you think about the vectors in this space, the vectors in this space might look like this. The first vector we can think of is just a vector 1, 1, 1. Vector V might be something like 1, 1, 0. Vector W is equal to 0, 0, 1. And if you think about this, you can see that we really are only going to have 8 elements in this vector space. Now, I keep saying that it's a vector space, but that means we need to think about vector addition. We need to think about scalar multiplication. Scalar multiplication works sort of the way you'd expect it to work, except the scalars here are not the real numbers. The scalars are, again, either going to be just 0 or 1, and that works out quite fine. But vector addition in this space works in a very odd way. So vector addition is component-wise, and it's done modulo 2. Modulo 2 is a fancy way of saying we do the following. We've got 2 possible entries, 0 and 1. And if you add 1 to 0, 0 plus 1 gives you 1. And then if we add 1 to 1, you get 0. It's sort of strange, right? This is sort of overflow and underflow problems. But this over here you can use to define vector addition. And if you define vector addition in this way, you can check for yourself that it is actually, in fact, first you might find it interesting to check the following. If you add V and W, if you add that vector V to the vector W, you get the vector U. But equally, if you add W to U, you get V. And if you add W to V, you get U. So this is some really weird looking behavior in some sense. It doesn't matter how you add them up, you get the remaining one. But you can use this definition of vector addition, and you can use scalar multiplication, scalars, let's just say. If you use this definition of vector addition and you use this definition of scalar multiplication, you should be able to show that this over here really is a vector space. And if you want to take a look at some of the details, just have a look at the notes. And this over here is actually really important. I'll be with you in a moment. It's really important for the theory of Hamming codes and for transmitting information and detecting and correcting errors in transmission of information. All right, I'm going to hang around now, so maybe it's better if you just come and speak to me at the front. All right, get to your next lecture.